So there's your learning goal: understand and apply the rules of taking a walk on a graph. That's what mathematicians actually say, taking a walk on a graph for this topic. And a walk is one of the definitions we'll talk about. And we have things that I find this quite hard because we have all these synonyms that mean different things, in my opinion. So we have trails, cycles, paths, they all mean different things. So I'm going to run through this, but I'm actually kind of reminding myself as I go because I'm learning this as well, these definitions. But you'll need to know what they are. So we've already considered some contextual application of graph, and we're going to talk about what exploring means now. This will lead to some mathematical problems. So there's a problem called Konigsberg Bridge, which is about trying to get around a graph crossing all 7 of these bridges in a certain town. And we use graph theory to prove that that can't be done. But that's different to another problem, which is a traveling salesperson problem. And that would be a situation where you might have 10 towns you need to visit. It could be a delivery problem. It could be anything at all where you're out and about. 10 towns or 10 locations, even on the Gold Coast. And you need to work out which is the best way to go to shorten my trip. How do I optimize this trip? And so these definitions are going to apply to different elements of those different problems. So here's my first question. I need to leave home and return home after visiting 4 places as shown. We're going to start by describing a sensible solution. Is it the only solution? And what do I mean by a sensible solution? So let's imagine that I follow this path here. I go from home to the library, from the library to the gym, from the gym to the shop, from the shop to the library, from the library to the gym, from the gym to the post office, and then home. Is that a sensible solution? It takes me to all the locations, so it meets the one criteria I've said. Would you like me to go through that path again? I go from home to the library, library to the gym, gym to the shop, shop to the library, library to the gym, gym to the post office home. Sensible solution? It's not really a sensible solution because instead of following this path, going home, library, library, gym, gym, shop, shop, post office, and home, which takes in each of the 5 vertices without retracing a path, I've chosen for some reason instead to go home, library, gym, shop, and then back to the library, and then gym and post office and home. And who knows, maybe on my adventure I get to here, I get to the shop and go, oh, this road's closed. I've got to go this way. Maybe I had to do that. Maybe I've got to retrace a path. There's a contextual reason perhaps. Perhaps I just have no idea how to drive myself around in a sensible manner. So that's kind of what I mean by a sensible solution. A lot of the problems that you face will be about minimising these paths and these distances or these situations. Right now we're not considering distances, but I would say if I was considering distances, I would probably go this way. Home, library, library, shop, shop, gym, gym, post office home. That to me seems like it's probably the shortest path along each of those paths there, but I'm just assuming that the scale is right. I don't really know. So the next question was, is this the only one? And the answer to that is no, there's going to be heaps of ways you can do this. There's enough paths there, there's heaps of ways I can do it. There are definitely 2 ways that I can do it in a sensible manner. If I go home, library, library, gym, gym, shop, shop, post office, and then back home, that's the other sensible route. And of course, I could reverse it. I could go to the post office first. I could have that other problem, which I sometimes do when I'm out and about in the Gold Coast on the weekend. I need to go to the shop, but I want to buy milk. I really want to do that last. Otherwise, I'm going to end up with warm milk in the car. So there's other things that come into it, and other criteria that might be set. Are there any questions on that? The main key thing that I wanted to bring up here was I'm going to define a whole bunch of mathematical stuff, but when you get into the problem sets or when you get into practice exams or exams, you're going to find a lot of the time what you're doing relies on a little bit of common sense to do with the criteria and the context. You've got to think about the context and what it means to be sensible within that context, and then apply the mathematical language that makes sense for that. So let's define some stuff. A walk is a route through a graph. We have notation that we apply to walk, so I can take a walk there. I've done it in green over on that graph, and that walk is A to B to C to D, and that's a walk on a graph. Okay, now you might hear them describe a random walk on a graph, and you'll be pleased to know that I was listening to a podcast on the weekend about the Abel prizes. They're like the Nobel prizes, but for mathematicians. The prize this year was won by a pair, two people, who were working on random walks and probabilities associated with random walks. So a walk in a graph is this. A random walk is if I walk from A to B, and then, well, actually it doesn't work because there's only one more route. I walk from B to E, and then I just get a dice and roll it. And I say, if I get a 1 or a 2, I'll go back to B. If I get a 3 or a 4, I'll go back to D. If I get a 5 or a 6, I'll go to F. And that's a random walk, completely randomised. And things like, what's the probability that it'll take me 7 walks before I cover all the vertices or something like that. And there's some really good, particularly in computability and computing logic, really, really good applications for that kind of stuff as well. So that's a walk. We define it A, B, C, D, or A, B, E, F, as in this case. A trail is a walk with no repeated edges, but it may have repeated vertices. So you don't have to cover all of the vertices, but a trail has no repeated edges. Once you've gone along an edge, you cannot go back over it. That's a trail. Whereas on the other hand, a path is a walk with no repeated edges or vertices. It takes it a step further. So you have a trail, no repeated edges, and a path, no repeated edges or vertices. Some point over the next week or so, you will want to create your own way of remembering this situation. And the best way is going to be to do a bunch of questions and remind yourself regularly, but you may also come up with some sort of summary in your own words that would help as well. Closed is a word that comes up. A closed walk starts and finishes at the same vertex. A closed trail is the same. A closed path is the same. So if a closed walk has no repeated edges, well, then it's actually defined as a closed trail. So the word walk is the catch-all, and then under that word walk, we have trails, and under that word trails, we have paths. And so they can all be defined in this kind of vertical setup. A walk is anything. A trail has no repeated edges. And then, so to get from a walk to a trail, that's what happens. And a path is a trail with no repeated, back to front, vertices. So just keep that in mind. That's our situation there. That's another way of looking at it. Any questions? Last little thing here is a cycle. So we've got a walk, a trail, a path. If a path is closed, so if you start and finish at the same vertex, do not repeat an edge, do not repeat a vertex, that's now called a cycle. And you'll see it inside a diagram here. If I do a cycle, which I'll do here in green, A, B, E, D, A, no repeated vertices, no repeated edges. It's called a cycle, and you can see it creates that sort of circular shape, or a shape that starts and finishes and makes a shape in itself. So that's called a cycle, and it's also a closed path, although mathematically we call it a cycle, so that's kind of annoying. You won't really see closed path come up that often, but you will see cycle come up in its place. So here's an example. I'll leave that up. I know some people are writing it down. On the graph below, describe a 1, closed walk, 2, an open path, 3, a cycle. And then in extension, what types of walks can vertex F be a part of? Explain your reasoning. Okay, shall I do them? Let's do number 1 first. I'll do this in green. So I'm just going to be one example. A closed walk. Remember, a walk can have repeated edges and it can have repeated vertices. So I might be really specific at making sure it's got repeated edges and vertices. but it's got to be closed. So I'm going to start at G and I'm going to finish at G. G, A, D, B, A, G. So G to A to D to B to A to G. Now, if I didn't have the graph, I can see that A is a repeated vertex. So it's definitely not a path. And I can see that GA is probably a repeated edge. But if this graph had multiple edges, so there was two ways of getting from G to A, it might not be, but it could be. So I'm suspicious there. I can see that information in there. That is a closed walk. Starts and finishes in the same location, nothing else matters. Any questions? Thank you. Thanks. Orange, an open path. So an open path, a path has no repeated edges or vertices. Open means it doesn't start and finish at the same spot. Let's make an open path. F, E, B, C. That'll do. F to E to B to C. No repeated vertices, no repeated edges, and it doesn't start and finish at the same spot. And a cycle, last of all, which I'll do in purple. A cycle is a closed path, so it starts and finishes at the same location, no repeated edges, no repeated vertices. So what I might do for this cycle is I might just go A to D to C to B to A, D, C, B, and then back to A, makes it a cycle, a closed path. Lastly, remember walks is the catch-all. What type of walks can vertex F be a part of? So if I start at vertex F, can that be a part of a cycle? Can anybody explain why it can't be a part of a cycle? Can't repeat an edge? Is that where you're heading? Okay, so we can't repeat an edge. So if I start at F, I have to go along here, and the only way to close this is to go back to F, but it will repeat an edge. So it can't be part of a cycle. Can it be part of a closed trail? Trails also includes not repeated edges. So in a trail, I can repeat a vertex. So the fact I'd have to go back to E would be fine in a trail, but then I'd still have to repeat edge FE. So it can't be part of a closed trail. Can it be part of a closed walk? It can be part of a closed walk because a walk doesn't matter about repeating edges. It doesn't matter about repeating vertices. So I can go F, E, B, C, D, G, E, F. And go back there. I've repeated one edge. I've repeated one vertex. It doesn't matter. It's a walk. And it can be part of anything that's open. So it just can't be. It's no to the cycle and no to the closed trail. Now, this is probably not a big enough fish to be a complex unfamiliar in any of the exams you take, but just look at what's happening here. When you get into the exercise, they're your standard questions. You'll get a graph that will say, is this a closed path or not? What is this? Or draw a closed path on here. They're your standard, simple, familiar questions. You see over here how this extension is written differently. It's written in a way it's not just you now recalling the definition of a path anymore. It's now you interpreting the problem and analysing the situation. So, and you should be talking about cognitive verbs in a lot of your lessons. If you find that you are interpreting and analysing, they are the higher level cognitive verbs, then you're probably working on complex familiar or complex unfamiliar. So just keep that in mind and look for the questions that are written differently and the ones that require you to do some interpretation. They're your higher level questions. Another example, and that's it then. In the graph below, classify each walk as either cycle path trail or closed trail. So none of them are just walks. Can anybody tell me? So a cycle is a closed path, don't forget. I've basically got path, trail, closed path, closed trail. Are any of those closed? Why none of them close? They don't go back to the same vertex. So they all start at A, none of them finish at A. So again, this might be a multiple choice question. Go, which one of these is a closed path? And you're looking at a list like that and there's a fourth option that starts at A and finishes at A, your job's done. You don't have to look any further. It's the only one that could actually be a closed path. So I doubt that's going to happen, but you might be able to wipe out some answers really quickly. So look for that. Anyway, A, B, F, D, B. A, B, F. Oh, what planet was I on? D, B. That's a walk through the swamp. Now, this B has a repeated vertex. So even if there was a bit there, this is a, oh, it's not closed, so this is a trail. Because it's got a repeated vertex, it cannot be a path. It has to be a trail. A, B, D, C. Let's hope this one's true. A to B to D to C. That one's almost closed, so I've gone too far there. That one's almost closed. If I went back to A now, that would be closed. But it's not closed, but it is a path. That's a, I don't know what's going on. A, C, D, B, F. A, C, D. A, C, D, B, F. Bless you. And this one is also a path. No repeated edges or vertices. Any questions? Can you define walk, trail, path, cycle, open, closed? Can you determine graphs of given walks and vice versa? Exercise 10D. We haven't even written all there, but basically you can do all the questions. There's not that many. And then we've got, I haven't got an additional exercise, but at some point I hope I will soon. We've got 25 minutes to knock it off.